Welcome. Welcome to this talk on Circular Crested Weir. My name is Hubert Chanson from the University of Queensland, based in Brisbane. Spillway on weir crest design controls the discharge capacity for an uncontrolled crest. Historically, spillway crests were thick for structural consideration, followed by the development of broad crest on circular crest in the mid-19th century, until the introduction of the Auger crest in the late 19th century, early 20th century. Auger crest, which, by the way, is optimized for one single design discharge. The photo here illustrates on the far right an Auger crest, and on the bottom a broad crest in operation. In the context of hydrological and hydroelectric extremes, like for example in Australia, where we had long-lasting droughts, but also extreme rainfalls, we need to ask the question whether it makes sense or not to optimize the spillway crest, namely an Auger crest, for one single design discharge, rarely used and too often re-evaluated. In that context, there would be a case for a circular crest design instead of an Auger crest, because a circular crest is more stable than a sharp crest overflow. It provides a larger discharge capacity compared to the broad crest, and it's much simpler to design and to build compared to an Auger crest, not to mention a need to pass the debris. And this would have been the position until 5 years ago. But 5 years ago, Professor Tullis, Dr. Crookston, and Professor Bung initiated a multi-lab challenging exercise under well-defined constraint to understand the level of uncertainty and dependency of such data on laboratory technique and instrumentation, including the circular crest design. Altogether, 20 hydraulics laboratories contributed to this exercise, and the outcome showed some challenging results, with a close agreement at low head, but massive data scatter at medium to large head, in particular in terms of the discharge coefficient, illustrated here with the dimensionless discharge coefficient as a vertical axis as a function of the upstream head above crest in dimensionless form, with the red data dashed area corresponding to the data scatter from the 20 laboratories, while the black symbols correspond to the experience at the University of Queensland, highlighting a non-linear rating curve with some hysteresis on data which depended upon the record durations, with differences whether the record took place over 1 minute or over 30 minutes. So the current contribution focused on the hysteresis, non-linearity, and instability of circular crested weir. The work was done experimentally based upon an undistorted flood similitude in a 0.4 meter wide channel over a very wide range of discharges, extending over 2 orders of magnitude, the range of instrumentation. The design of the circular crested weir was identical to the design introduced by Professor Tullis and his colleague. Looking at the basic flow features, starting from small to medium discharge, we observe first an attached nappe, and with increasing discharge, we see the detachment of the nappe, and for high head, the reattachment of the nappe on the downstream wall of the circular crested weir. If we looked at the upstream water depth and downstream water depth as a function of the discharge, experiments show very little difference whether we are increasing or decreasing the discharge, with basically a monotonic increase in upstream and downstream water depth as a function of the discharge. But for the same data set, if we looked at the water depth above the crest and we are on the dimensionless discharge coefficient, we see a massive data scatter linked with some hysteresis on non-linear behavior, we found this slide, experimental data obtained with increasing discharge in blue, and experimental data obtained with a decreasing discharge in red. These instabilities are linked to the fluctuation of the impingement perimeter of the lower nappe, illustrated on this video. While this particular movie illustrates the gradual closure of the air cavity, followed later on by a sudden reopening. We see the closure of the cavity, and then its sudden opening. While this movie, which is a high-speed video movie recorded at 240 frames per second, replayed at 30 frames per second, illustrates the air cavity filling, and we are going to see shortly the cavity filling as the air from within the cavity is progressively entrained at the impingement perimeter of the lower nappe. And then there is a disappearance of any air bubble, and we have a reattached nappe. For such transitory condition, this graph illustrates the time series of the water depth above the crest over 100, nearly 2,000 seconds. And what we see is the superposition of large fluctuation with fast fluctuations. And if we looked at the air cavity size, with on the top the height of the air cavity, on the bottom the surface area or the volume of the air cavity, we see instabilities associated with the transition from attached to detached nappe. All this observation illustrate a slow cavity filling, and in contrast, a very rapid, transient, sometimes very violent cavity opening. Such sudden change in the nappe flow condition are associated with change in flow condition. With a detached nappe, we have a lesser discharge coefficient and higher upstream water level, rather than with an attached nappe, we have a much higher discharge coefficient. And in turn, this cyclic behavior from attached to detached nappe can lead to fluctuation in the upstream water level with potential upstream reservoir slushing, change in water discharge with the generation of downstream surge wave, vibration to the weir, and loud noise. These instabilities have direct implication in terms of experimental and numerical modeling of circular weirs. It highlights, for example, the importance of the record duration. Traditionally, physical modeling is performed with 1 to 3 minutes recordings, while the present experiment illustrates the need for a minimum of 30 minutes of records for these transitory conditions. Such transient behavior is rarely well understood by engineers, but also by their clients, despite their importance because of the generation of very violent fluid structure interaction. They are basically never reproduced numerically using commercial software on most CFD package working on desktop workstation. We need to wonder whether such good industry practice are really good enough for such complicated flow. In conclusion, the circular crested weir is a very simple, efficient, stable overflow system, but which may be characterized at medium to high height to hysteresis and instabilities associated with a cyclic behavior with nappe detachment and nappe attachment, leading to data scatter, non-linearity occur, and hydrodynamic instabilities. This work illustrates the need for long-duration experiments of this cyclic behavior with direct implication in terms of weir operation and weir modeling, emphasizing also the need for quality in experimental and numerical setup, not to mention expertise of the modelers, as well as the limitation of the vast majority of numerical models. This work has been presented at the HWRS 2022 and is available as a peer-reviewed conference paper. Additional relevant references are listed here. Thank you very much.